Hey guys, welcome to Electronics. I'm Gregory, and in this video we are talking about BJT, reverse bias, base-emitter junction noise sources. We have this very simple prototype of a BJT generating noise followed by a chain of amplifiers. So let's understand together how this circuit behaves. How can we measure noise using a spectrum analyzer? Even more important, how can we automate the measurements using scripts in the computer? We also gonna look at very important aspects of noise like noise temperature and excess noise ratio, ENR. So prepare your coffee and come with me. This is the prototype that we're going to use on this video for experimentation, and we see here that we have a power supply input, we have a BJT transistor here, that is actually our DUT, or device under test, where we have the base-emitter junction reverse biased. The stream pod controls the amount of reverse current in the base-emitter junction. We directly excite a first amplification stage, a common-emitter amplifier. The signal follows into the chain to the next amplifier, and this is the output, an SMA connector to be connected on the spectrum analyzer. You see here that I also have a third stage of amplification, but this is not used in this example because two stages of amplification were enough to get the noise level that I need for my setup. So why we have this prototype, this little PCB here? I'm working on a project where I need a noise source, and I'm gonna talk about this because I think it's very important for you to understand my line of thoughts to arrive at this board here. This is my first attempt at noise generation, so I didn't have any background, any practical understanding about how noise sources and reverse biased base-emitter junctions behaved. So I made this little board as an experimentation. Come here to the bench to grab this practical understanding about the behavior. When you feel that you don't understand something, go there and build. So you have the thing in your hands, you can test it, you can measure it. And this is why I constructed this with 3 stages of amplification. Because I had no idea, no baseline about the amount of noise I would get from the base-emitter junction. And with 2 amplification stages, I got exactly what I needed, 2.5 volts peak to peak. Very interesting characteristic of noise is that it doesn't have a time frame. Look at this. It doesn't matter the time frame, it looks exactly equal. Very interesting. Thank you so much, Keysight, for sending me this amazing little unit here. For the application that I'm using, this is enough to know that I have the correct peak-to-peak voltage, and it was enough to see on the oscilloscope that the noise was noisier enough. But as I had this board, I got interested to understand better how we can characterize noise. I did a lot of experimentation and wrote an article about this. The link is in the description of the video. You can take a look there. We have 2 things that are very important when we talk about noise. Noise bandwidth. What's the bandwidth of this noise? A perfect white noise source has all the frequencies. This means that if we look in an spectrum analyzer, we are going to see energy, power, up to the highest frequency we can measure with our tooling. And the other aspect is the amount of noise we are generating, the noise density. When we talk about noise, we don't talk much about power, we talk about density. Because noise is not a single frequency, it's not a single spectral line. Noise is something that spreads over frequency. So we talk about the amount of power per unit of bandwidth, dBm per hertz. This is something that we are going to look on this video. Another important thing is excess noise ratio. How much noise we are generating over the thermal noise baseline, negative 174 dBm per hertz, the thermal noise floor. That's the amount of power generated by a 5th ohm resistor when measured at room temperature in a bandwidth of 1 Hz. Can you see why bandwidth is so important here? Why we need to talk about density, power density? Because as noise spreads over frequency, a white noise source has energy over every frequency we analyze. The amount of noise power we get is proportional to the bandwidth that we are using to look to the noise. If we increase the bandwidth of the measurement, we are going to measure more absolute noise power. As we are collecting more frequency beams, you see, that are available from this noise source. We are looking to the noise using a broader lens. I connected again the noise generator to the oscilloscope so we can see this behavior. This RMS voltage measurement here is actually measuring this an RMS. What means to be an RMS measurement is the equivalent voltage of a DC supply that will deliver the same amount of power than this random signal is delivering over the bandwidth of the measurement, 100 megahertz, because this is a 100 megahertz oscilloscope. And we can see that if we limit the bandwidth of the oscilloscope, so let's go here to bandwidth limit. Look what happens. Because we are limiting the bandwidth to 20 megahertz, so with a reduced bandwidth, we get less absolute power from the noise. If we could decrease even more the bandwidth, we would see the signal becoming smaller and smaller and smaller as the bandwidth was reduced. The heart of this circuit is a reverse biased base-emitter junction from a BJT transistor. We have a transistor here with the collector unconnected. Here in the base, we extract the noise, AC coupled. We have a trim pot, a trimmer, to adjust the amount of current, reverse current, that we are applying to the base-emitter junction. The current here is the reverse current that's being used to bias the base-emitter junction, and this resistor here to isolate the emitter from the VCC, and we can AC couple the emitter here to ground. So the AC path for the signal, here the noise is a signal, is this path here. You see? So when we measure the noise here, we are measuring exactly the noise over the reversed bias base-emitter junction. Now we have the noise generator connected to the spectrum analyzer, properly terminated to 5th ohm. In the example using the oscilloscope, it was not. Now it's properly terminated. And we're gonna turn on here the power supply. We see this roll off here. A lot of power here at lower frequencies, less power at higher frequency. And for the video, we are leaving with this spurious here, that is the signal from my wireless microphone. Why we have this shape? This actually is the shape of the amplification chain. The noise spectral shape mainly comes in this case from the frequency response of the amplification chain. We see here actually the roll-off of the amplifiers. The reverse base-emitter junction excess noise actually is much more flatter than this shape here we see on the spectrum. One very important point here, guys, is that this is not power density. What we are measuring here with the spectrum analyzer is the power at each frequency. This is not the proper way for characterizing a noise generator, a noise source. If I change the bandwidth of the spectrum analyzer, you are going to see that the power we are measuring is changing. What's happening is that the spectrum analyzer is a receiver that's changing its tuning as it sweeps in frequency, measuring the amount of power at each frequency and displaying it as the trace in the spectrum analyzer. So if we change bandwidth, the resolution bandwidth of the spectrum analyzer, we are going to change the amount of power we are measuring. As I explained before, when we look to noise, when we measure noise, the amount of power that we measure is proportional to the bandwidth of the measurement. Configuring the spectrum analyzer as an example for 300 kHz resolution bandwidth, it means that the spectrum analyzer is sweeping a 300 kHz filter over the spectrum and measuring the power. If we change the resolution bandwidth to 100 kHz, the measured power will go down because now the spectrum analyzer is sweeping a 100 kHz filter over the spectrum. This is why a spectrum analyzer, a modern spectrum analyzer, has the noise marker. The noise marker just compensates the reading for the bandwidth that's configured in the spectrum analyzer. Let's see this. If we take a marker here, let's define 100 megahertz as our default measurement here, okay? We are measuring an amount of power at 100 megahertz. If we reduce the resolution bandwidth, we are going to measure less. You see, negative 39 negative 40 dBm. If we increase the resolution bandwidth, we are measuring more power, of course, because we are changing the bandwidth of the filter that the spectrum analyzer is sweeping over the spectrum. So for proper measuring noise, we need to use the marker function noise marker. Look at this. Clicking here, now the amount of noise displayed is a unit of power over hertz, over frequency, over bandwidth. Negative 95 dBm per unit of hertz. This is power density. It's not power, not absolute power. It's the amount of power contained in a 1 Hertz filter, 1 Hertz bandwidth. The trace changed a little because when we enable the noise marker, this device here, this spectrum analyzer, changes a little the configurations of the sampling mode and other things to make a better noise measurement. This is why it changed a little the looking of the trace. But what matters is that now we are compensating for the bandwidth of the measurement. So if I change now the resolution bandwidth, look how the density here is not changing. The trace is changing, of course, but the spectrum analyzer is compensating this displayed value here to always display the power density, the power over units of frequency. I got excited studying noise. How noise behaves? What is excess noise ratio? How can we calculate this? So I decided to test and to characterize different transistors. And there on the article you can see I characterize 4 RF transistors that I had here. All the measurements were done using automated measurement. And this is a very important thing. Tooling. When I need to repeat measurements, there's nothing better than automate the measurements when you need to get guaranteed and stable results. And this is an advantage of using modern equipment. We can automate easily using scripts in the computer. So for characterizing the noise densities of the different transistors, I'm using a script that controls the spectrum analyzer. It configures the spectrum analyzer always to the correct parameters for the measurement, correct resolution bandwidth, video bandwidth, amount of averages. It configures the marker for noise function. It waits for the end of the averages, and after that it sweeps the marker manually by the automated script. It goes into 5 MHz steps, getting all the data and saves in a JSON file. Let's start a new measurement. First thing is configuring the device for the correct measurement. All the parameters are configured and the measurement is started. Now the script is doing averages using the purple trace. It's gonna do 6 averages, and after the averages we see it sweeping the marker, reading the noise density at each position in 5 MHz steps. A measurement setup like this guarantees that we are getting always the same result. And guys, don't get me wrong, I'm not saying that you're gonna perform the measurement in the wrong way, but when you need to measure like 4 transistors, each transistor with 3 different current levels. If you add all the permutations of the readings, you're gonna see that for characterizing and for having proper data for analysis, we need to make hundreds of measurements sometimes. And of course, we are going to make mistakes if we need to do hundreds of measurements. So it's important from an engineering perspective and from a practical perspective to invest the time in the tooling. I really love to design good tooling, because after that the measurement and the execution becomes much easier. And after having all the data stored on the computer, we can analyze. As you know, this video was made possible by all the patrons of the channel. Thank you so much. So all these script files are available on Patreon. If you are a patron, you can download it there. So guys, as an example here, I have a script that's gonna read the capture data and plot the noise density and also the noise temperature here. Now that we have the data on the computer, we can transform the data to better analyze it. So we see in blue the line that we were seeing on the spectrum analyzer, and here the same data plotted as a noise temperature in Kelvin for a bandwidth of 1 Hz. Guys, we have a video here on the channel that actually was made in partnership with Keysight about noise and noise temperatures, signal to noise ratios also. If you don't know what a noise temperature is, go there, watch the video, you're gonna like it. That captured trace was the noise density here on the output. This noise density we are reading here is the noise density of the junction generator here, amplified by the amplifier chain, shaped by the gain profile of the amplifier chain. And of course, with the noise of the amplification steps, the noise figure, as I explained in the video I was talking about, with the added noise figure of the amplification stage. Here, for a noise generator, the noise figure of the amplifiers doesn't matter much because they are adding noise and we want noise in the output. I added also in that PCB an SMA connector that's tied to this node here, right? So I desoldered the transistor, removed the transistor, and now we have full access to injecting a signal here to measure the response of the amplifier using the tracking generator of the spectrum analyzer. So you can see on the article that we have the gain profile of the amplifier. So I was able to de-embed the gain of the amplifier to plot the input referred noise. The input referred noise is the noise that we are getting here referred to the input of the amplifier, this node here. The input referred noise here is very similar, it's a very similar measurement, not equal, but it's a very similar measurement to the noise, the raw noise that we are getting just from the transistor, the base emitter of the transistor here, acting as a noise source. So measuring the gain of the amplification stage, we are able to approximate the noise generated by the transistor itself. And if you see on the article, you're gonna see that it's very, very flat, much flatter than the full response, because what dominates the shape we are seeing on the spectrum analyzer is the shape of the gain function, the transfer function of the amplifier. As an example, we see here the noise density is measured for a BFR 106, a common RF transistor, for 3 different reverse currents. The measurement seems to follow common sense, as higher currents generates higher noise densities, as a higher current adds more entropy to the system. You can see, guys, that we have here a comparison for other transistors. The BFR 92A was the noisier that I could find here on the lab. And as we talked about, we can measure the gain of the amplifier using the tracking generator of the spectrum analyzer, injecting the tracking generator in the place of the noise PN junction. And we have here the orange trace, that is the gain of the amplifier chain. Now that we have the gain, we can subtract this gain from the noise density to arrive at the input referred noise. And here we see the input referred noise. We see that the responses are very flat, and we also see that the noise density generated by the junction is very low. It's not so high as I expected. We can plot this data as noise temperatures in Kelvin. We see that the BFR 92A has a much higher noise temperature here in a linear scale, right? And the excess noise ratio of each base emitter junction can be calculated from the temperatures. What is the excess noise ratio? Is how much this noise generated is in excess from the baseline, the thermal baseline of the system at room temperature. In this example, we see the BFQ67 at 1 milliamps generates a noise profile that is 30 dB over the thermal noise floor of negative 174 dBm per Hertz. A very important aspect of measuring noise using the spectrum analyzer is that what we are actually measuring is the combined noise power density of the measurement device, the spectrum analyzer, and the DUT. In this case here, the transistor base emitter, reverse biased base emitter junction. So this response that we get from the spectrum analyzer, when we think from the perspective of noise temperatures, is the summation of the noise temperature generated by the transistor, by the DUT, and by the spectrum analyzer. And actually what happens is that spectrum analyzers are very noisy. People don't think about that, and this is not our perception when we think about spectrum analyzer. But if you see the architecture of a spectrum analyzer, it has a lossy mixer, it has a step attenuator on the input. All of this adds to the noise figure of the spectrum analyzer that can be as high as 25 dB. Spectrum analyzer contributes a lot to the measured noise. One thing we can do that helps a little to compensate, it's not perfect, is to measure the baseline noise floor of the spectrum analyzer, doing exactly what it did with the automated test, but connecting the spectrum analyzer to a 5th ohm load to measure the baseline noise floor of the measurement setup, and we store that measurement. After that, we characterize our device, doing again an automated measure. We can transform both measurements to noise temperatures, just converting the dBm per hertz noise density to a noise temperature in respect to a 1 hertz bandwidth, and we can subtract both to compensate for the noise floor of the spectrum analyzer. And this follows because TBE, the temperature, the noise temperature of the base-emitter junction that we are trying to characterize, is approximated by the final temperature measured subtracted by the temperature of the measurement device. So we do this compensation for each measurement point, and after that we can get this trace here that is in the noise temperature domain and convert it back to a power density in dBm per hertz. And I did exactly this on the article. As I just explained, all the measurements were corrected by the noise floor of the spectrum analyzer. So here we have the captured data with a noise marker of the noise density generated by the spectrum analyzer when connected to a 5th ohm load. We see that it generates a noise density over 35 dBs higher than the thermal noise floor, the expected thermal noise floor. This trace was converted to a noise temperature, and it was subtracted from all the measurements. So here we have the noise temperatures in a logarithm scale and the noise temperature of the spectrum analyzer here. This is the noise temperature generated by the measurement setup. Subtracting the noise temperature floor from the measurements and converting it back to noise densities, we can have here the corrected measurement. And we see that the corrections are more important when the two lines approach, when the noise temperatures have similar magnitude. Of course, when the DUT has a much higher noise temperature, we don't see a deviation from the original measurement and the corrected measurement, because the DUT in this region here is generating orders of magnitude more noise than the spectrum analyzer. But this is not the case at higher frequencies, when the two noise temperatures become similar. And here we see a deviation between the original measurement and with the measurement corrected by the noise floor of the equipment. The transistor here is a BFR92A, and I'm biasing it with something in the range of 500 micro to 2 milliamps. I'm doing that adjusting this trimmer here. Supply here is 8 volts. Why a transistor connected like this generates noise? This is not exactly a property of a transistor. It's a property of any reversed bias PN junction. The base emitter is a PN junction, and we are using it here as a Zener diode. You see, the collector here is disconnected, so the collector base junction is not used. We are using this transistor as a diode that is connected in reverse. For RF transistors like this one here, the reverse voltage here, the reverse breakdown voltage, is something like 4.5 to 5.5 volts. So this reverse PN junction is actuating in the Zener region by Zener effect. Some transistors will have a reverse bias voltage higher than this, like something near 7 volts. In this case, the PN junction is working more in the breakdown avalanche mode by the avalanche effect that actually generates more noise. In practice, we don't have one effect or the other effect. We have a combination of both. For this transistor here, we are more on the side of the Zener effect, but of course in practice a little of breakdown avalanche is also happening in this case, contributing to the generation of noise. What follows here are two stages of amplification with common-emitter amplifiers. These transistors here are BFR 106, 106. Here you have 608 ohms, 68K. Quiescent current here something like 5 milliamp. So here the noise amplitude is higher, is amplified, and we follow with another stage. And you saw that on the board I etched 3, but I used only 2 because I got the amount of noise amplitude that I needed with only 2 stages. So the reversed bias base-emitter junction here is generating a noise density. So the spectrum here is something like this, not so flat. And this is a power density, is a power by unit of frequency. And the total absolute power that we get here on the output comes from the power density generated by the noise junction that is amplified by the transistors and that is constrained to the bandwidth of this circuit. So let's say that this circuit here has a bandwidth of 100 megahertz. The power present here on the output is the integration of the power density generated by the noise source multiplied by the gain of the stages over this range of frequency here, is the integration of this curve. If you are asking yourself why the reverse PN junction generates noise, you can search and study for shot noise. What happens is that we are applying a reverse potential over the PN junction, and the electrons that are crossing the junction that have enough energy potential to cross the reverse bias junction are quantized amount of energy. Each electron is actually a quantized amount of energy. So this quantization effect, when looked here from the perspective of an electrical circuit, looks like noise. All the electrons crossing the junction potential are modulating the voltage over the PN junction in a discrete and randomized way. We don't know when an electron gonna jump the barrier potential, and we actually don't know how many electrons gonna jump in an amount of time. The only thing that we know when looking to this as an electrical circuit is that in the average we have this amount of current, reverse current, that is physically an amount of electrons jumping the PN junction potential in an average term. But in practice, this flow of electrons is random, and this modulates the voltage here randomly, generating white noise. The only thing that we can control is the average aspect that is represented here by the reverse current. That's actually fascinating. Go read about shot noise. Well guys, I hope you enjoyed this video. If so, subscribe to the channel and give it a thumbs up. Remember that you can support the channel becoming a patron, link in the description. See you in the next video of All Electronics.